retrospect part, this is a sort of a brief history of TESS in a single slide in terms of things that we actually did. There's some smiles of amusement by some of the members of the audience that TESS, the idea related to TESS actually started out at a TESS conference when Dave Latham and I had a conversation to try to repurpose a small satellite that MIT had built previously. And it was called TESS, and that was the idea. And then this actually turned into a proposal that we put together to the Calder Foundation and to a number of other private funding agencies that we would actually be able to do a TESS-like mission with the resources that they could bring together. And then, you know, the markets changed and some people who weren't quite as wealthy anymore. So we actually said, okay, let's try this out as a SMEX. And then the SMEX was actually proposed in 2008, and then that was not selected. We came in second. The organization that actually finished first was never went on to fly, so I don't know whether that means we should be happy about being second or not. And then finally, it was proposed in 2011 in its current form, and that's what we're all going to be talking about today. So TESS has really continued to enable a very high rate of discovery as a result of what we can see from the papers that the mission has actually enabled. And I think there are three primary reasons for why TESS has been able to enable such a flourishing of results. The first one is we really released the data without any proprietary period, and that was part of the idea from the very beginning. The unprecedented high eton-do means that not only will TESS provide a lot of information related to exoplanets, which is in the name, but time domain and multi-messenger astrophysics is really part and parcel of the way that the instruments are actually configured. And then finally, these so-called cameras really are 64 million exquisite CCD photometers, and they have these 4 characteristics that are listed in this slide, and that is really, to my mind, one of the key enabling technologies that we really went for on TESS. Everything related to the instrument has been working flawlessly during this 6 years that we've been operating, and that's really a testament to the skill and dedication of everyone who worked on the mission for the hardware. The publication rate from TESS observations continues to accelerate. This is a bar chart that shows that we're approaching 2,000 publications, and in fact in 2024 we've actually gone beyond that. And most of these are related to general astrophysics, but there are, you know, 1/3 of them are related to exoplanets per se. And here's a way to actually look at how TESS is done. You know, the cliche is TESS punches above its weight compared to 4 other NASA missions. As you go across on the x-axis in time, you can see when TESS turned on in 2018. And the notable thing is the slope that is in the publication rate that we've achieved. In fact, if you then extrapolate this to 2024, to the date that we have right now, there's more publications, and if you take this year's rate through today and you extrapolate to the end of the year, we can expect to have about 850. So the bottom line is that we're approaching the Hubble publication rate in the early part of the next phase of TESS extensions, we hope. Okay, now, how does TESS manage to provide all this information? First of all, it has an enormous field of view. It covers a little bit more than 5% of the entire sky at any given time. And if you actually look at what a TESS camera sees, this is one camera out of the 4. It's an area of the sky 24 degrees on the side. And so what's shown here is just one of the 4 cameras. The moon would fit in, 10,000 moons would fit in this. The Kepler field of view was 100 square degrees or 105 square degrees, and it fits within one of the CCDs. And then if you look at some of the other initiatives that are ongoing, this is where ZTF stands. This is what LSST's field of view would be with approximately 10 square degrees. And then this is the wide field imager for Roman. So the graphs we each time do of TESS is really the secret sauce that makes the mission behave as it does. And then with the 200-second exposures and the full frame images, we're able to produce more than 10,000 successive images with 200-second resolution every observing sector of 27 days. So that to me are the 2 of the things that have been so critical in the success of the mission. Now there's also been a progression in the science data downlink capability that we've been able to configure for successive mission extensions with TESS. The cartoon that's shown now shows how TESS was configured in the Prime mission for 2 years. There were 2 contacts near perigee, and we had 30-minute FFIs. Then in the next extended mission, we reduced that time to 600 seconds, and then in the current extension that we're operating on, the FFIs have been reduced to 200 seconds, and we've also introduced 20-second targets as well as a prompt methodology called TICA that Michael Fastow was largely responsible for, working on that with Chris Burke. And then for the upcoming mission extension, we anticipate that we'll be able to provide these same modes, and then in addition, we're talking about having 2-second targets as well as some real-time samples that are associated with an interval when we normally achieve only engineering data. This is the so-called HASO section that's shown, I guess, right here, these 4 contacts. Okay, now, so then if we consider the sky coverage in the successive mission phases, Roland Vanderspek will be talking about some more of this in greater detail than I will. We've achieved the coverage of the sky that's shown in these maps on the right-hand side, and there's some cleanup on some of the gaps that are going on in the current extended mission. But all in all, the sky coverage is better than 97% at least once, 84% twice, and about 2/3 of the sky at least 3 times. And that'll be the case after September 2025. One of the key things that has enabled TESS to have the success that it has was this choice that we made of a P/2 lunar resonant orbit. Now this orbit is stable. It's stabilized by the Kozai-Litoff mechanism, and that was something that we actually planned. And this chart actually shows the changes that take place in perigee, and those oscillations are related to the effects of Jupiter in a minor way, the moon, and the sun as well. And this stable orbit behavior is anticipated for about 100 years. And if you actually see just what's shown here for 25 years, then these are where the missions that we've had so far with TESS since the launch in 2018 fall. And then for another question often comes up is, well, how long might TESS last? It has propellant for that's needed for maneuvering, and that is something that works out to be certainly far greater than 100 years, because there's 29 kilograms left, and it's one gram per month. So you can do the arithmetic. It's a long time. It's more than anybody in this room will ever think about being around for. So for the 122nd and 22nd target utilization, this is a table that Roland is actually going to discuss in more detail in his next talk. But the one thing I wanted to focus on is that the director's discretionary time slots have been dramatically undersubscribed. And the number of DDT programs, for example, in EM2, there have been 28 so far for the 22nd mode. And the thing I just urge everyone to be aware of the fact that this opportunity exists. The only thing you have to be sure of is that the proposals have to be submitted 6 weeks or so before the start of the sector in order to be scheduled. But it's very little overhead in terms of actually doing this, and the directions are on at the MIT website. Okay, in terms of where we actually stand today, this is a sky map that gives the status that we have for the TESS objects of interest. These are exoplanet candidates. There's 543 that are on the exoplanet archive that was updated just in the last few days. That's 543 handily beats the TESS mission requirement by an order of magnitude. And there also have been more TESS planets with measured masses and radii than was the case for the Kepler mission and K2 separately. So the follow-up observing program, Dave Latham will be discussing. This has been an incredibly successful initiative, and has involved the organization by Sam Quinn and Karen Collins and the group at CFA, and it's just been a marvelous success, and you'll be hearing a lot of that as the program goes on. One other thing is that TESS data are in high demand by the community and in other ways that have reflected the volume of data that we've had to deposit and have made available at this Space Telescope Science Institute masked archive. The users have been downloading this data at an incredible rate. This is a plot of the holdings versus the data demand. And the two little dots that are encircled in this are those for JWST and TESS, and the one that's sort of down around 5 o'clock, that's Hubble. So you know, it's been really successful in making the data available for the community. And then for the high-level science products, the HLSPs, this is the area of this diagram where they actually lie. And the Quick Look pipeline and the Goddard Eleanor Light programs and the TESS SPOC and the TGLC, which was a format that has come into recent use, is another way in which we can exploit the data. And this is another map that actually shows the download rate, and these are the 5 forms of the data that have been most attractive to the communities. Okay, now TESS is enabling a broad range of non-exoplanet astrophysical discovery areas, and the check marks on this mean that there are TESS results that have occurred in every one of these topics during years 1 through 6. We'll be hearing a lot more about that as the conference goes on. And then just looking ahead, another thing is what might be new with future missions that are coming up. Plato certainly is going to be an important contributor to future progress. And this map shows the so-called LOBS S2 field near the south ecliptic pole for EM. If you look at where TESS could look, this has not been set, during that period of time, this is the way it would actually look if we were to observe in 55-day sectors. If you wanted to work with shorter sectors, you just have to make more maneuvers, but basically by turning this diagram, you can see that it's possible to cover the entire 7,000 plus square degrees that encompass the field that's been selected for Plato. Now, the extended pointings at the north ecliptic pole, or the south, in the case of Plato, the south ecliptic pole, can have another series. There's a series of advantages that I think will be considered by the TUC and in discussions that we have here, that are shown here, that are shown in this list. And there are a number of possible plans that are in discussion, and there have been suggestions already from the community as to how some of these things might be worked out. The one idea might be to do the south ecliptic pole in cycle 8, and then the north ecliptic pole to a much deeper degree, while Plato is observing the south ecliptic pole, and the missions would be complementary in that respect. And then the other thing that we're talking about is to do more frequent downloads of the TICA-derived special intervals to support other missions. That's already been done for things like gamma bursts as well. So this is a timeline that shows where we are. This is where we are in Extended Mission 2 in terms of the other programs that are underway, and this is where we will be with regard to those programs. And especially in EM3, the Rubin Observatory will come into its own. There's going to be another series of observations from LIGO. Ultrasat is going to launch, and of course there's Plato and the work that's going to be going on with the ground-based extremely large telescopes, and of course Roman. So the other thing I'd like to end by showing this slide of the members of the first TESS Users Committee. Most if not all these people are here, and they're going to be a vital contributor to our planning in the future. And we welcome them and plan to provide as much information as we can to enable their work. Roland is actually going to give a briefing for the Users Committee meeting on Thursday that's actually related to some of the things that we can and cannot do with the satellite from the point of view of practicalities. And so I'd like to stop at that point and be happy to answer your questions.